that blurry smudge you see in the sky on certain nights. If you know where to look, in the constellation of Andromeda, far from any light pollution, is the closest galaxy to us. 1,000,000,000,000 stars. A disk 220,000 light-years in diameter. The most distant object visible to the naked eye from Earth, at 2.537 million light-years. It's hurtling toward us at 110 kilometers per second, and in 4.5 billion years, it will slam into us head-on. Tonight, we're reconstructing the greatest cosmic catastrophe our galaxy will ever experience, and answering the real question: will Earth survive? The answer will surprise you, because a collision between two galaxies is absolutely not what we imagine. The Andromeda Galaxy, Messier 31 in Charles Messier's catalog, NGC 224 in the general catalog, is a barred spiral galaxy like ours, but significantly larger. Its diameter is about 220,000 light-years, compared to 100,000 to 120,000 for the Milky Way. It contains about 1,000,000,000,000 stars, 1,000 billion, more than triple the number of stars in our galaxy, according to current estimates. It is surrounded by a halo of diffuse matter that extends for 1,000,000 light-years and already overlaps, in its outermost regions, the halo of the Milky Way. For a long time, Andromeda's exact trajectory remained uncertain. We knew it was approaching. Its spectrum shows a blue shift, the signature of an object moving closer. But we didn't know whether the trajectory was strictly head-on or slightly offset, which could have meant a near miss rather than a collision. In 2012, a team led by Roland van der Marel of the Space Telescope Science Institute used Hubble data accumulated over 7 years to measure Andromeda's proper motion, its sideways drift relative to the line of sight. The result, published in the Astrophysical Journal, a head-on collision is confirmed. This is not a near miss. The two galactic cores are heading straight toward each other. The current approach speed of 110 kilometers per second will accelerate as the mutual gravity of the two galaxies pulls them in. At the time of the first major contact, in about 3.75 billion years, the relative speed will be on the order of 400 kilometers per second. To understand the context, we need to talk about the local group. The Milky Way and Andromeda are not isolated. They are part of a set of about 50 galaxies gravitationally bound within a volume roughly 10 million light-years in diameter. The two dominate this group by mass. The rest consists of dwarf galaxies, the large and small Magellanic Clouds, the Sagittarius Dwarf, the dwarfs of Ursa Major, Draco, many of which are already in the process of being absorbed by one or the other of the two giants. The large Magellanic Cloud, visible to the naked eye from the southern hemisphere, is spiraling toward the Milky Way and will probably be absorbed in a few billion years. It's no surprise that two galaxies dominating the same group end up merging. Gravity is inexorable on cosmological timescales. The dark matter halos of the two galaxies, invisible but massive envelopes that extend far beyond the visible stellar disks, are already interacting. The dark matter of the Milky Way and Andromeda has been slowing each other down for billions of years, dissipating orbital energy and making the collision inevitable. The timeline, established by van der Marel's simulations and since updated by other teams, is as follows. In about 2 billion years, Andromeda will begin to visibly distort Earth's night sky, a gigantic crescent of diffuse light spanning several tens of degrees. In 3.75 billion years, the first close pass, the two galactic disks cross through each other for the first time. In about 4.5 billion years, the main collision. In 6 billion years, the merger is complete. The two spiral galaxies have ceased to exist separately and have produced a single elliptical galaxy. Astronomers have already given it an informal name, Milkomeda. The instinct when faced with the phrase collision of two galaxies is that of total disaster. Stars crashing into each other, explosions, everything burning. That image is physically incorrect, and understanding why reveals something fundamental about the structure of matter in the universe. A spiral galaxy is mostly empty space. Take the Sun. Its diameter is about 1.4 million kilometers. The nearest star, Proxima Centauri, is 4.24 light-years away, or 40,000 billion kilometers. If we shrink the Sun down to a sphere 10 centimeters in diameter, an orange, Proxima Centauri, at the same scale, would be another orange about 2,800 kilometers away. The distance from Paris to Moscow, and between the two, near absolute emptiness. This proportion is typical. In the Milky Way, stars are microscopic objects immersed in abysses of interstellar vacuum. When two galaxies pass through each other, the stars of one galaxy slip through the spaces between the stars of the other. The probability that one star directly strikes another over the entire duration of the galactic merger is tiny. Numerical simulations give figures on the order of a few direct stellar collisions for the whole merger, out of the hundreds of billions of stars involved. Essentially zero on the galactic scale. What actually happens during a galactic collision is governed by gravity, not by physical impacts. The gravitational forces of the two galaxies distort their respective disks over hundreds of millions of years. The spiral arms stretch, twist, fragment. Streams of torn-out stars, called tidal tails, extend for hundreds of thousands of light-years into the surrounding space. The ordered geometry of the two spirals gradually breaks down. The most spectacular phenomenon associated with galactic collisions is the compression of interstellar clouds of gas and dust. When two galaxies pass through each other, these clouds, far less compact than stars and therefore far more prone to interactions, collide, compress, reach densities and temperatures sufficient to trigger gravitational collapse and star formation at an unprecedented pace. These are bursts of star formation, or starbursts, with star formation rates that can reach hundreds to thousands of solar masses per year, versus 1 to 2 solar masses per year normally in the Milky Way. We can observe this process in real time in other galactic systems. The antennae, NGC 4038 and NGC 4039, are two spiral galaxies in collision about 45 million light-years away in the constellation Corvus. They began interacting about 900 million years ago. Images from Hubble and the James Webb show two still distinct galactic nuclei connected by streams of stars, tidal tails stretching tens of thousands of light-years, and regions of intense star formation lighting up the zones of gas compression in thousands of young, bright clusters. What we see in the antennae is a snapshot of a process that the Milky Way and Andromeda will reproduce on a larger scale in a few billion years. At the heart of each galaxy lies a supermassive black hole. Sagittarius A star, at the center of the Milky Way, contains about 4 million solar masses. Andromeda's central black hole is estimated at about 100 to 230 million solar masses, depending on the studies, about 25 to 60 times more massive than ours. During the galactic merger, these two black holes will follow their own paths within the merging galaxy. First separated by tens of thousands of light-years, they will gradually draw closer under the effect of dynamical interaction with the surrounding stars, a process of dynamical friction that dissipates their orbital energy on timescales of tens of millions of years. Eventually, probably several hundred million years after the main galactic merger, they will form a compact binary system, orbiting each other at distances of a few light years, then a few astronomical units. The final phase of this binary merger, when the two supermassive black holes collapse into one another, will be the most energetic event in the local universe since the Big Bang. The energy released will be emitted largely in the form of gravitational waves, distortions of space-time that will propagate at the speed of light in all directions. The amplitude of these gravitational waves will be detectable from cosmological distances. If instruments like LISA, the ESA's future space-based gravitational wave detector, scheduled for the mid-2030s, still exist by then, they would capture this signal billions of years earlier from other galaxies to which the same thing would be happening. Two black holes that merge literally make the fabric of space-time ring like a cosmic bell. The question everyone wants to ask: will Earth be destroyed? The direct answer is probably not by the galactic collision itself. For the reasons mentioned earlier, the immensity of interstellar space, the probability that the Sun will enter into a direct collision with another star over the entire duration of the galactic merger is less than 1%. Even if a star passes close to the Sun, say within a few light years, the gravitational effects on the inner planets of the solar system would be minor on short timescales. Earth could pass through the entire galactic collision without any star striking it directly, without the Sun being catastrophically disturbed in its orbit. But the galactic collision will redistribute the stars. The merger of two spiral galaxies into an elliptical galaxy transforms an organized rotating structure into a diffuse structure with no spiral arms, with stars distributed more randomly in all directions. The Sun, currently in a spiral arm about 26,000 light-years from the galactic center, will be subjected to the gravitational forces of the merger, and its position in the resulting galaxy will be redistributed. The most detailed numerical simulations of this merger, notably those by van der Marel and by Cox and Loeb published in the Astrophysical Journal, give several possible scenarios for the Sun's fate. In the majority of simulated realizations, the Sun ends up in the merging elliptical galaxy, but in a position very different from its current one, perhaps 2 to 3 times farther from the center. In about 12% of the simulations, the Sun is ejected completely into intergalactic space, wandering alone in the void between the galaxies of the local group. If the Sun is ejected, Earth's night sky, if an inhabited Earth still existed, would be unrecognizable. No visible Milky Way, that luminous band that crosses our current sky and testifies to our position inside a galactic disk. Instead, near total darkness, with only distant galaxies as blurry smudges. A sky of absolute solitude. If the Sun remains in Milky, the night sky will be different in another way. Elliptical galaxies no longer have spiral arms. No more of those concentrations of bright young stars that light up the Milky Way's arms. Milky's night sky will be more diffuse, less structured, with a more homogeneous distribution of stars. Far fewer active nebulae, far less star formation. A calmer, older sky. But here is the point that the plan highlights correctly, and that must be emphasized clearly. Andromeda is not the main threat to life on Earth. Our own star is, and much earlier. The Sun's luminosity increases by about 1% every 100 million years, as the accumulation of helium in its core accelerates fusion reactions. In about 1 to 1.5 billion years, some 3 billion years before the collision with Andromeda, the additional solar radiative forcing will trigger a runaway greenhouse effect on Earth, gradually evaporating the oceans and rendering the surface uninhabitable for all complex life. Earth will become a Venus, hot, dry, shrouded in a dense atmosphere of water vapor and CO2. In about 5 billion years, the Sun will exhaust its central hydrogen and begin to swell into a red giant, potentially reaching the vicinity of Earth's current orbit. The collision with Andromeda, which will occur within that interval or shortly thereafter, is a cosmically spectacular but secondary event for the fate of life on Earth. Complex life will have disappeared from Earth's surface long before the first visible effects of the galactic merger. 4.5 billion years. That is the length of time separating us from the main collision. To put that number in perspective, anatomically modern humans, Homo sapiens as we define ourselves by our skeletal morphology, have existed for about 300,000 years. Agriculture is about 12,000 years old, writing 5,000 years. The industrial era, 250 years. The space age, 70 years. 4.5 billion years represents 15,000 times the duration of our species' existence. Non-avian dinosaurs reigned for 165 million years, about 4% of that span. Complex multicellular life has existed for about 600 million years, 13% of that span. Life itself on Earth dates back about 3.8 billion years, and we are already 85% of the way. Assuming that humanity, or something descended from it, will still exist in 4 billion years, is to assume a continuity longer than anything that has existed in the history of life on Earth. It is an assumption that exceeds our capacity for extrapolation. But if we did it, what would such a civilization see? In long-term survival scenarios, several steps are necessary. In less than 1 billion years, leave Earth. The surface will become uninhabitable long before the galactic collision. Colonize other bodies in the solar system, then other stellar systems. In several billion years, a civilization that has mastered the energy resources of an entire galaxy, a Type 3 civilization on the Kardashev scale, would be able to observe the galactic collision from optimal positions, perhaps from artificial structures at safe distances. What it would see, over hundreds of millions of years, would be the greatest spectacle in the local universe. 2 giant spirals slowly interpenetrating, slowly on a cosmic scale, but representing speeds of hundreds of kilometers per second for the objects involved. Entire regions lighting up in bursts of star formation, creating thousands of stars per year in zones of gas compression, bathing regions of the merging galaxy in an intense blue light. Tidal tails stretching over hundreds of thousands of light years, carrying millions of stars torn from their original positions. And at the heart of all that, 2 supermassive black holes drawing inexorably closer before their final merger, which will produce the most powerful gravitational wave signal ever emitted in the local group since the Big Bang. This spectacle, no civilization will ever see a comparable one in its own history. Galactic collisions happen regularly in the universe. They are the rule, not the exception, on cosmic scales. But from the inside, experienced over billions of years, they represent something unique in the experience of a living species. Galactic collisions are, on the scale of the universe, the way galaxies grow. The Milky Way itself is the result of past mergers. Gaia data from ESA, which mapped the motions of more than 1 billion stars in the Milky Way, revealed the dynamical signatures of at least one major past merger. A galaxy called Gaia Enceladus, or Gaia Sausage, absorbed about 8 to 10 billion years ago. The stars of our galaxy's halo carry in their orbits the memory of that event. We ourselves are the product of a collision. In several billion years, all the galaxies of the local group will have merged into a single mega-elliptical galaxy. And the accelerated expansion of the universe, driven by dark energy, will continue to push all other galaxies away. Milky and the remnants of the local group will be permanently isolated from the rest of the observable universe, a gravitationally bound cosmic island in an increasingly empty universe. What we call our galaxy has never had fixed borders in time. It will have even less in the future. An inevitable collision in 4.5 billion years. Two galactic nuclei that will pass through each other several times before merging. Two supermassive black holes that will collapse into one another, releasing an energy unmatched in the local universe. The Sun probably ejected from its current position, perhaps even out of the galaxy. And Earth, perhaps physically intact through all that, but uninhabitable for a long time because of its own star. Andromeda will not destroy us. It will transform our galaxy into something new. And that is exactly what the universe has been doing since the beginning. It destroys to create. The Milky Way as we know it, its spiral arms, its nebula, its flat and orderly disk, is a transient configuration in a 13.8 billion year history of mergers, ejections, accretion, and transformation. Tonight, if you look up and find that small, fuzzy patch in the September and October sky, slightly above the W-shaped constellation Cassiopeia, remember, it is coming, slowly, inexorably, and it is magnificent.
The Andromeda Galaxy, also known as M31, is linked to our own Milky Way galaxy. They are neighbors, sometimes even twins, and destiny will bring them together in a few billion years' time. Andromeda is fascinating because it lies so far away, yet is easily visible to the naked eye. In fact, it's the most distant object you can see without an instrument. Its visual magnitude is 3.4, which explains why it is visible from Earth. This visibility is facilitated by its large size. It covers an area of the sky 6 times the size of the full moon. It lies more than 2 million light-years away. This distance, established in the 1920s, makes the universe much larger than previously imagined. For a long time, it was thought to stop at the limits of the Milky Way. The best time to observe it in the northern hemisphere is in early autumn, between August and September. At this time of year, it is visible all night long. In the southern hemisphere, it's more likely to be seen between August and December. The Andromeda Galaxy was first described by the Persian astronomer Abd al-Rahman al-Sufi in 964 in his Catalogue of Fixed Stars. He referred to it as a small cloud. The first observation of the galaxy through a telescope was made in 1612 by the German astronomer Simon Marius. It was first photographed in 1887 by Isaac Roberts, a British engineer with an interest in astronomy, who became a pioneer in nebula photography. Mistaken for a nebula, it found its way into Messier's catalog as M31. Andromeda's spiral structure is clearly visible in the photos. Long called the Great Andromeda Nebula, it was listed as a galaxy in 1923, after 3 supergiant variable stars were photographed within it. Calculations then confirmed that these stars were extragalactic objects and part of a new galaxy. In 1912, the American Vesto Melvin Slipher succeeded in measuring its radial velocity. It is approaching the Sun at a speed of around 300 kilometers per second, for 190 miles per second. If we take into account the motion of the solar system in the Milky Way, we can say that the two galaxies are approaching each other at a speed of 100 kilometers per second, or 60 miles per second. The galactic nature of Andromeda was definitively established in 1929 in a study published by Edwin Hubble. Today, thanks to the Hubble and James Webb Space Telescopes, we continue to deepen our knowledge of this galaxy. We can confirm that this is a barred spiral galaxy just like the Milky Way. Its name comes simply from the fact that it lies in the constellation Andromeda. According to the ancient Greeks, Andromeda was the daughter of Cephe and Cassiopeia, the royal couple of Ethiopia. M31 is one of the largest objects in the sky. It is the nearest spiral galaxy to the Milky Way and the largest member of the local group. The local group, whose diameter is 10 million light-years, is a group of some 60 galaxies to which the Milky Way also belongs. It is part of the Virgo supercluster or local supercluster, a group of around 100 galaxy groups and clusters, stretching over 100 million light-years. It is itself part of an even larger supercluster called Laniakea, from the Hawaiian words immense and sky. Laniakea has a diameter of over 500 million light-years and is thought to contain 100,000 large galaxies. M31 is more than twice the size of the Milky Way, with a diameter of around 220,000 light-years. It is thought to contain around 1,000 billion stars, or 2 to 5 times more than our galaxy. I told you Andromeda was a spiral galaxy. You may already know that there are 4 main types of galaxy. Elliptical galaxies. These are spherical or oval in shape, with no internal structure, and roughly uniform brightness. The stars move in a disorderly fashion, preventing them from falling towards the center of the galaxy. Spiral galaxies. Lenticular galaxies. These can be described as a mixture of spiral and elliptical galaxies. They have a bulky nucleus and a disk, but no spiral arms, and their interstellar medium is rather poor. Irregular galaxies. These are all galaxies that do not fit into the previous 3 types. They are often misshapen in appearance and very rich in gas and dust. They include the Magellanic Clouds. As the Andromeda Galaxy is a spiral galaxy, let's take a closer look at it. A spiral galaxy contains several hundred billion stars and looks like a disk. This disk contains a luminous spherical bulge at its center, called the bulge. Surrounding this disk is a halo of stars grouped together in globular clusters. In a spiral galaxy, the disk contains several luminous arms. This light is emitted by the young stars these arms contain. These arms wrap around the center, giving the galaxy its spiral shape. The Andromeda Galaxy, like our own, is a barred spiral galaxy. It has a large central bar formed by a band of stars, with the ends of the bars being the starting points of the arms. There are various hypotheses concerning these bars, which are found in 2 out of 3 spiral galaxies. The current hypothesis is that the structure of these bars acts like a stellar nursery. It is thought that the bars act as a mechanism that feeds gas into the inner chains of the spiral. They are linked to the center of the galaxy and the movements and pressures that take place there. This would explain why a bar is not always the same size when observed. Spiral galaxies, which resemble enormous whirlpools, are considered among the most beautiful celestial objects. There where stars are formed, they're very dynamic. You'll see that they're full of astonishing things. There'll be plenty of excitement on our journey. Stars are distributed throughout the galaxy according to their age. The disk contains mainly young stars, while older stars are found in the center and halo. Like most galaxies of this type, Andromeda contains a supermassive black hole at its center. Long thought to be much more massive than the Milky Way, Andromeda's latest estimate is 825 billion solar masses. This figure is regularly revised. You now have an idea of what awaits you on this journey. Before we move on to our first stop, let's take a look back in time. According to scientists, the Andromeda Galaxy formed 3 billion years ago. Only, you say? Well, compared to the Milky Way, it looks pretty young. Remember that our galaxy has existed for at least 12 billion years. Thanks to ingenious calculations, modeling, and simulations, it appears that the Andromeda Galaxy is the result of a collision of two galaxies. A first galaxy was already present 7 billion years ago, when a second crossed its path 4 billion years ago. The latter was 4 times smaller than the first. This accidental encounter caused the two galaxies to merge, giving rise to the Andromeda Galaxy. Today, this merger allows us to understand the distribution of the galaxy's components, especially those located in the halo. The halo is made up of giant star streams, dust shells, and diffuse clusters. The star streams and dust shells come from the smaller galaxy, while the diffuse clusters and disk deformation come from the larger one. This explains why the latter structures are more abundant in heavy elements. The more massive progenitor naturally provided more elements. M31's youth explains why its characteristics are so different from those of the Milky Way. In our galaxy, stars follow fairly regular orbits, whereas in the main disk of the Andromeda Galaxy, stars over 2 billion years old follow disordered trajectories. Giant streams of stars halo the galaxy on either side. These structures do not appear to be stable over time, so they must be recent. Before arriving at your destination, you'll have time to admire the space landscape. As I told you, the Andromeda Galaxy lies a long way from us, some 2.55 million light-years from our Sun. Imagine if such a journey were possible. Imagine being able to travel that far at the speed of light. After half an hour's travel, we can already see Jupiter, 628 million kilometers or 390 million miles from Earth. Admire its beautiful ochre colors and rings, as well as some of its satellites such as Io with its intense volcanic activity and Europa. Continuing our journey, we pass Saturn and its famous rings. 1,428 million kilometers or 880 million miles further on, we pass the beautiful ice giant Uranus. 28 moons orbit this superb blue planet. Further on, after another 1,628 million kilometers or 1,000 million miles, we come across another magnificent blue planet, Neptune. The temperature here is very cold, but it's its largest moon, Triton, that holds the temperature record. On its surface, it's minus 237 degrees Celsius, or minus 394 degrees Fahrenheit. We now leave the solar system, crossing its boundary, the heliopause. You're in for a bumpy ride, so hang in there. We're now in interstellar space, yet still a long way from our destination. We're still in our galaxy, the Milky Way. Now, 4.2 light-years from the Sun, you can see the star Proxima Centauri. It's the star closest to Earth after the Sun. It's accompanied by Alpha Centauri, a double star visible from the southern sky. Nearby, you'll have the chance to catch a glimpse of Proxima b, a recently discovered exoplanet. Its orbit lies within Proxima's habitable zone, which has scientists excited about the possibility of finding life there. Of course, several conditions are necessary for this to happen, starting with the presence of water. Let's leave the search to the scientists and move on. Let's travel another 4 light years. We're now approaching a star 20 times brighter than the Sun, located in the constellation of the Great Dog, Sirius. We're now 8.6 light years from Earth. You've already had your fill of it, but you're wondering when you're going to arrive. Just wait a little longer and admire the constellations and nebulae we pass along the way. After passing through the constellations of the Unicorn, Gemini, and Giraffe, we're now in Andromeda. Can you see its A shape? One of the branches of the A is often represented by Andromeda's leg, since the name of this constellation comes from the name of this young girl. According to legend, she was chained naked to a rock, only to be devoured by a sea monster. Rest assured, she was saved by Perseus. Take another look at the star Ross 248, 10 light years from Earth. It's a dark red dwarf with a temperature in excess of 3,200 degrees Celsius, or 5,800 degrees Fahrenheit. It is still undergoing nuclear fusion, with hydrogen being transformed into helium. Enjoy this unique spectacle. Not far from the Ross star is the Gliese 15 stellar and planetary system. This system comprises 2 stars and 2 planets. Its stars, GJ15A and GJ15b, are variable stars that orbit each other. Its planets are a super-Earth and a super-Neptune. Interesting, isn't it? Look ahead, here we are. That beautiful spiral you see before you is the Andromeda Galaxy. We've just crossed 2.5 light years, and yet the journey has only just begun. Let's take a look at the stars that cohabit the galaxy, since they're the ones you'll see most easily. Studying M31 brought to light a new class of variable stars, the LBVs, or Blue Luminous Variables. They were discovered by Edwin Hubble and Alan Sondage in 1953. These are giant stars with masses up to 150 times that of the Sun. They are very rare. But above all, they are stars within M31, whose brightness varies perceptibly over very short periods of time, just a few years. They are also known as Cepheids. Cepheids are extremely important to astronomers, helping them to determine distances. They are, as you well understand, very bright, and their period of variability is linked to their peak energy production. To measure a galaxy's distance, the scientist measures the periods of a Cepheid. He then compared the maximum brightness observed with that of Delta Cephei, a variable star in the constellation Cepheus, which served as a reference for the calculations. This is how Edwin Hubble and his team determined the distance to Andromeda in the 1920s. They can shine thousands of times brighter than the Sun, approaching the theoretical upper limit of stellar radiation. This limit, also known as the Eddington limit, is a brightness value that a celestial object cannot exceed. If it does, gravity becomes insufficient to counterbalance the radiation pressure, and the star breaks up. To avoid exceeding the limit, variable stars constantly eject matter, thus decreasing their mass. This is why they are surrounded by nebulae resulting from these explosions. Eta Carinae is the closest and best studied example. It's a stellar system comprising at least 2 stars, located in the constellation Carinae. These stars have very short astronomical lifetimes, just a few million years. This is due to their high mass and luminosity. They can evolve into Wolf-Rayet stars before going supernova. A Wolf-Rayet star is an extremely hot star of several tens of solar masses, which for a very short period expels the matter surrounding its core in the form of stellar winds, leaving the latter bare before exploding in a supernova. In the Andromeda Galaxy, known blue variable stars include AF Andromedae, AE Andromedae, M31 V15, and VA1, among the first luminous variable stars to be discovered in M31. AF Andromedae is an irregular variable, both in period and amplitude. Its mean apparent magnitude is around 16, with brightness variations of the order of 1 magnitude. Its irregular variability occurs over a period of several years. It is subject to significant mass loss. AE Andromedae was not studied until much later in the 1970s. Its first spectrum was published in 1975. It is also variable in period and amplitude. Its average apparent magnitude is around 17. It produces intense solar winds resulting in ejection velocities of 100 kilometers per second, or 60 miles per second from its outer layers. There are intrinsically variable stars whose radiation and variability depends solely on them. Intrinsic variables include pulsating, rotational, and eruptive variables. There are also extrinsic variable stars whose variability is caused by external properties such as rotation. These include optical variables and cataclysmic variables. But the Andromeda Galaxy is thought to have around 1,000 billion stars, at least twice as many as our own galaxy. Some even believe the figure to be higher. Let's take a look at their distribution. Andromeda is richer in stars than our own galaxy, and therefore brighter. It is 25% brighter than the Milky Way. But the Milky Way gives birth to more stars, so it's gradually catching up with its twin. Andromeda consists of a thin disk surrounded by a thicker one. The thin disk contains the youngest, most stable stars. Researchers believe that at the time of Andromeda's creation, they were still in the form of gas and therefore undisturbed by the original collision. Older stars in the thick disk, on the other hand, have a more chaotic motion. The Andromeda Galaxy also abounds in star formation, thanks to the high presence of carbon monoxide and molecular hydrogen. These two gases are essential for star formation. It is thought to contain some 460 globular clusters, which, as you know, contain hundreds of thousands of stars. These stars are moving at dizzying speeds. Starting from the galactic center, their speed increases at 225 kilometers per second, or 140 miles per second, before decreasing to 50 kilometers per second, or 30 miles per second, at 7,000 light-years, then increasing again to 250 kilometers per second, or 155 miles per second, at 33,000 light-years, before dropping again to 200 kilometers per second, or 125 miles per second, at 80,000 light-years. As you can see, stars can be found all over the galaxy, but depending on where they are located, they vary in age and type. The FAT project, Panchromatic Hubble Andromeda Treasury, counted 117 million individual stars in the Andromeda Galaxy. Its aim was to produce a detailed map of the galaxy. It exploited the Hubble Space Telescope's 3 imagers in infrared, visible, and ultraviolet. The researchers then assembled the 7,398 images like a mosaic. These thousands of shots were taken between July 2010 and October 2013, but the result was unveiled in January 2015. The resulting image covers only a quarter of the Andromeda Galaxy, but it's 100,000 pixels wide. Individual stars can therefore be distinguished. It was from this image that astrophysicists understood that Andromeda was born at the collision of two galaxies around 3 billion years ago. The 117 million stars surveyed cover an area of 61,000 light-years. This mapping has provided new insights into the star formation process, thanks to the use of infrared images. Using the color of the stars, it has been possible to determine their age and reconstruct the history of the galaxy over the last 500 million years. The American astronomers were in for a surprise. They discovered that the 10,000 PC ring, a star-forming ring thought to be transient, has actually existed for 500 million years. Since it takes a large amount of fresh gas to form stars, the region must have had a significant supply of gas. Scientists have also seen that a large wave of newborn stars travels from one side of the galaxy to the other. All these findings suggest that a major event affected the galaxy several billion years ago: a collision. In 2016, the European-funded EXTRAS project announced the discovery of the first rotating neutron star in the Andromeda Galaxy. Researchers made this discovery by analyzing data provided by the European Space Telescope XXM Newton. A neutron star is made up of small, extremely dense remnants of a massive star that exploded to produce a powerful supernova. They are the remnants of stars that have finished evolving. They come from stars that were once very large, receiving 4 to 8 times the size of the Sun, before exploding in supernovas. The outer layers of the star are thrown off into space, but the central core remains without producing nuclear fusion. The star collapses in on itself. They are incredibly dense, with a mass 1.5 times that of the Sun, and a diameter of just 20 kilometers or 12 miles. Neutron stars have a high rotational speed and can send regular pulses of radiation towards the Earth. Seen from our planet, they appear to blink. Although they are very common in the Milky Way, where they number over 100 million, none have ever been observed in the Andromeda Galaxy. It rotates around its axis with a period of 1.2 seconds and seems to feed off a nearby star that orbits it in 1.3 days. This star, also known as a pulsar, is located in the outer arm of M31, most probably within a globular cluster. Further observations are needed to learn more about it, and certainly to discover others. Enjoy this starry sky as we head towards the center of the galaxy, the bulge. The bulge is the central part of a galaxy located in the disk and surrounding the galactic nucleus. Compared to a city, the bulge would be the ancient historical center. The Andromeda Galaxy is unusual in that it has a double nucleus. It was the Hubble Space Telescope that revealed this double structure in 1993. P1, the primary core, and P2, the secondary core, are 4.9 light-years apart. P1 is the brighter. Scientists have struggled to grasp the exact nature of P1. At first, they thought it was the residual nucleus of an ancient cannibalized galaxy, but calculations have shown that such a structure would not hold in the vicinity of a supermassive black hole as large as the one of the Andromeda Galaxy. It would have scattered it under the effect of tidal forces. They then hypothesized that a second black hole at the center of P1 would have stabilized this structure over the long term, but the distribution of stars in P1 does not argue in favor of its existence. It seems more likely that P1 is an accumulation of stars at the apoapside of their orbit around the galaxy's supermassive black hole. Apoapside? It's the point in a celestial object's orbit where the distance from the focus of the orbit is greatest. P2 contains the famous black hole, which is 40 times the mass of Sagittarius A, the black hole at the center of our Milky Way galaxy. This enormous figure corresponds to 110 to 230 million solar masses. In photos taken by the Hubble telescope, the black hole is surrounded by a mysterious blue color. It's a disk of hot young stars. This is rather strange, as young stars are normally found far from the center of a galaxy. There are over 400 of them, formed around 200 million years ago. They are concentrated in a disk only 1 light year across and are moving at the extraordinary speed of 1,000 kilometers per second. This disk is enveloped in a cocoon formed by a ring of old, very cold red stars. The stars and star clusters in the bulge of the Andromeda Galaxy are up to 8 times more enriched in heavy elements than the Sun. Let's take a look at this galactic center using infrared. We can make out a multitude of rings, including one located 33,000 light-years from the center. This ring alone contains most of the galaxy's dust and much of its gas. Why is it only visible in the infrared? It's made up of cold dust with a temperature below minus 258 degrees Celsius or 432 degrees Fahrenheit. This dust is only visible in the infrared. Infrared has also highlighted the fact that the bulge is box-shaped, which would make the Andromeda Galaxy a barred spiral galaxy just like the Milky Way. The bar is seen in the direction of its greatest length. Let's take a closer look at this supermassive black hole. It is generally accepted that all galaxies have a supermassive black hole at their center, but only those in the Milky Way, Andromeda, M32, and a few galaxies outside the local group have actually been observed. As we saw before, M31 is said to have a mass of 230 million solar masses. This is enormous. The intensity of light in the vicinity of this monster doesn't vary much, which means it feeds steadily. A simulation carried out by the scientists showed that a small disk of hot gas could form near the black hole and feed it continuously. This would explain its apparent calm. Do you remember what a black hole is? It's a region of space whose gravitational field is so intense that it prevents any form of matter or radiation from escaping. It is said to be created after the death of a very massive star. This is called a supernova. The star's core collapses in on itself, causing the outer layers of the star to be expelled in a gigantic explosion. All the remaining matter is concentrated in a tiny point called a singularity. The black hole swallows everything that passes too close to it, even light, which is why we can't really see it. Researchers guess its existence by observing the motions of bodies orbiting near its edges. Black holes often feature an accretion disk and jets created by the absorption of stars and gas. And these are clearly visible. The limit that must not be crossed is called the event horizon. It's a pretty name for a terrifying zone, since beyond this horizon you can't go back. But the more massive the black hole, the colder it gets. Andromeda has at least 35 other black holes discovered by the Chandra Space Telescope. In 2021, scientists identified an intermediate black hole in the globular cluster B023 G078. This is the most massive globular cluster in M31, with an estimated mass of 6.2 million solar masses. It is located on its periphery, 2.5 million light-years from us. The mass of this black hole would be 100,000 times that of the Sun. An intermediate black hole lies between a stellar black hole and a supermassive black hole. Its mass is between 100 and 100,000 times that of the Sun. Until this discovery, they were still hypothetical. Researchers suspect the existence of this black hole within the globular cluster B023 G078 because without its presence, stars would move more slowly. It could be a remnant of galaxy mergers. This intermediate black hole would be the remains of the smallest galaxy, which has fallen into the largest. The third type of black hole is the stellar mass black hole. It is formed by the collapse of a massive star, and its mass is between 10 and 100 times that of the Sun. Let's continue our journey to a more peaceful location. Since Andromeda is a spiral galaxy, it has arms, like its sister galaxy, the Milky Way. Let's explore them. The arms are difficult to see through a telescope, as they are very blurred and not very bright. To see them, you need to take photos with a long exposure time. Andromeda is a spiral galaxy, which means that the arms wrap around the center and form the spiral. But, unlike the Milky Way, some of Andromeda's arms look surprisingly like rings. These arms are thought to have appeared around 900 million years ago, when Andromeda collided with the nearby dwarf galaxy M32. This hypothesis was born of a simulation carried out by astrophysicists. Before the collision, Andromeda was certainly a disc-shaped galaxy with no arms. Today, M32 is embedded within M31. The gravitational interaction between the Andromeda Galaxy and M32 would have caused waves, which would have become Andromeda's spirals, giving them this ring-like shape. This is underlined by the dynamism of Andromeda's molecular clouds. Molecular clouds are interstellar nebulae of sufficient density and size to allow the formation of molecular hydrogen. M32 moves from the edges of Andromeda towards its center, then back again, sustaining the waves. All this takes place over billions of years. When we look at pictures of the galaxy, we see two large spiral arms, but there are 7 arms more or less developed. The two most visible arms are separated from each other by a minimum of 13,000 light-years. The 2 inner arms are richer in dust, while the others contain hot blue supergiant stars. Andromeda's arms are dotted with HII regions, i.e., regions of ionized hydrogen. These are emission nebulae made up of clouds that are 90% hydrogen, with most of the atoms ionized. The remaining 10% is helium and a few traces of heavy elements. It is hydrogen that gives them their characteristic red color. They extend over several light-years. HII regions have only been detected in spiral or irregular galaxies. They can be found just about anywhere in irregular galaxies, but as you can see, they are located in the arms of spiral galaxies. A large spiral galaxy may contain several thousand of them. Ionization is produced by the proximity of very hot stars that radiate strongly in the ultraviolet, ionizing the surrounding gas from which these stars formed. These clouds of ionized gas are visible at great distances. HII regions are not only sites of star formation, but also appear to contain planetary systems. The study of these extragalactic HII regions is essential for determining the distances and chemical composition of other galaxies. The Orion Nebula in our own galaxy is a well-known HII region. The arms of Andromeda give birth to many new stars, even if Andromeda seems to be at a standstill in terms of star production compared to the Milky Way. It's these stars that give the beautiful blue light in photos of the galaxy. Come, I'll show you a place to observe all this. In the southwestern arm of the galaxy, there's a star-forming region called NGC 206. NGC stands for New Regular Catalog, another catalog that lists nebulae and star clusters. NGC 206 is an open cluster where young blue stars are born and live. It was discovered by astronomer William Herschel in 1786. Isn't it magnificent? It contains over 300 very bright stars. It has a double structure. The region around its edge is around 10 million years old and includes several HII regions. The more central part is 40 to 50 million years old and includes a large number of Cepheids. The two regions are separated by a band of interstellar dust. The youngest massive stars are no more than 10 million years old. Much larger than the open clusters in our galaxy, NGC 206 spans some 4,000 light-years. Its size is comparable to that of the giant stellar nurseries found in neighboring M33, or in the Tarantula Nebula of the Large Magellanic Cloud. The bulge is surrounded by a giant disk which contains the arms we've just mentioned. When viewed under infrared light, at least two concentric rings can be seen, whose centers appear to be offset from the galaxy's true center. They can only be seen in the infrared because, as in the bulge, they are probably composed of cold dust, not visible to the naked eye. Scientists believe that the disturbances in these rings are related to the absorption of M32's peripheral layers. Seen from afar, the disk is not as flat as one might expect. It undergoes a torsion that seems to be linked to nearby celestial objects, notably the Triangulum Galaxy. In this disk, all the stars over 2 billion years old are undergoing disordered motions on a very large scale. This magnitude is comparable to their rotational motion around the galaxy's center. Only a recent collision can explain the restlessness of the stars. The Andromeda Galaxy is one of 3 spiral galaxies among the 60 or so in the local cluster. The others are the Milky Way and the Triangulum Galaxy, also known as M33. M33 is located around 2.8 million light-years from our galaxy. It is thought to contain 40 billion stars, and its mass is around 5% that of M31. Its diameter of over 50,000 light-years makes it the 3rd largest galaxy in the local group. It is visible to the naked eye under the right conditions. Its structure can be observed from Earth without being hindered by interstellar gas and dust. Andromeda has a multitude of stellar streams, stellar shells, and other debris from all recent interactions. This so-called tidal debris is so extensive that it joins the Triangulum Galaxy via a bridge of gas and stars, more than 10 galactic radii long. Andromeda, like all galaxies, also contains nebulae. A nebula is a celestial object composed of rarefied gas, plasma, or interstellar dust. They are the remnants of a supernova. You know that a supernova is a gigantic explosion that takes place when a star disappears. There are different types of nebula. Emission nebulae, which radiate light from the gas of which they are composed. Their hydrogen atoms are excited by the powerful ultraviolet light from surrounding stars. The hydrogen is then ionized, generating the nebula's luminosity. Reflection nebulae, made up of immense clouds of dust and hydrogen that reflect the light of nearby stars. They are often characterized by a blue light. Reflection and emission nebulae. Emission nebulae are often mixed with reflection nebulae. This is the case of the famous Orion Nebula. Supernova remnants, which group together very extensive nebulae in emission, formed in one of two ways: by the implosion of a dying supermassive star whose core no longer generates energy and collapses in on itself, by the explosion of a white dwarf in a binary star system, which has sucked in the matter from the accompanying giant star. Among the most famous of these are the Crab Nebula and the Swan's Laces. Their lifespan is fairly short for celestial objects. Wolf Rayet bubbles. These are emission nebulae found around certain stars of the same name. Regions of ionized hydrogen. Both types of nebula are bright. Dark nebulae, which are clouds of cold gas and dust that emit no light because they hide their stars. Planetary nebulae, which are shells of gas ejected by stars at the end of their lives. These are among the most beautiful celestial objects for all astronomy fans. They combine bold shapes with extraordinary colors. They shine against the black background of space. The first planetary nebula to be discovered was the Dumbbell Nebula, in the constellation Petit Renard. Observed by Charles Messier in 1764, it is recorded in his catalog as M27. Planetary nebulae, which have nothing to do with planets, are objects of low brightness, invisible to the naked eye. Nebulae are the remains of dead stars, but they are also the cradles where the next generation of stars will be born. New stars are regularly born within these nebulae. In 1885, a major event was observed by the Roon Observatory, a supernova. It remains the only supernova observed in the Andromeda Galaxy, and the first since the invention of the telescope. A century later, astronomers in Arizona have described the matter expelled at several thousand kilometers per second during this enormous explosion. This was supernova afterglow, which spread out into space to form a supernova afterglow nebula. They deduced that the supernova was caused by a white dwarf unable to absorb the gravitational collapse. This afterglow will dissipate in a few 100 million years. In the meantime, it offers us a magnificent spectacle. Like the Milky Way, the Andromeda Galaxy is surrounded by a gigantic halo. It is so large that it meets the halo of our own galaxy. It measures 1.3 to 2 million light-years in some directions. If it were visible to the naked eye, it would cover nearly 100 full moons. It's a reservoir of gas that enables the formation of future stars. Researchers were able to map this giant thanks to data transmitted by the Hubble telescope, which, as you know, is capable of observing ultraviolet light. By measuring the radiation from some 20 quasars located around Andromeda, they were able to estimate the dimensions of the halo, based on the amount of light it let through. The Andromeda Galaxy, by virtue of its large size, makes it possible to use this method. They also found that the halo is made up of two main layers. The inner layer is smoother, hotter, and more dynamic. It extends over some 500,000 light-years. Its composition appears to be the result of the impact of supernova activity. Simulations suggest that the halo formed at the same time as the galaxy. This hypothesis is confirmed by the detection of heavy metals, heavier than helium, resulting from the recent death of a star. It is estimated that over the lifetime of M31, half of the heavy elements produced by stars are ejected from the disk and end up in the halo. Understanding the halos that surround galaxies not only gives us a better grasp of past events, but also enables us to predict the future. Observations made between 2008 and 2014 in Hawaii show that the Andromeda halo is populated by gigantic streams of stars. The most prominent of these is called the Giant Star Stream. It appeared when the two galaxies that gave birth to Andromeda merged. We've talked about quasars, but what are they? They are supermassive black holes at the center of an extremely luminous region called the active galactic nucleus. They are even the most luminous entities in the universe. The visible part is not the black hole, of course, but the compact region surrounding it. Quasars are thought to gain in power through the accretion of matter. They are therefore made up of three main parts: the supermassive black hole, which contains almost all its mass and forms its center; the accretion disk, formed by matter falling towards the black hole. The friction between gas and matter in this disk causes temperatures to rise sharply. Jets of gas that are expelled from the accretion disk can reach speeds approaching that of light. Some believe they form when two galaxies collide, releasing immense amounts of energy. In 2006, there were 113,666 quasars, all very distant from us. The nearest is around 783 million light-years away, the farthest at the edge of the observable universe around 13 billion light-years. In 1932, Edwin Hubble was the first to identify globular clusters in M31. He discovered 140 of them. Today, there are an estimated 460 globular clusters associated with the Andromeda Galaxy. The brightest of these was photographed by Hubble and named G1 for Globular 1 and Mayall 2. It is also the brightest cluster in the local group. A globular cluster is a large ball of light containing thousands of stars. Mayall 2 contains around 300,000 old stars. It orbits Andromeda, 130,000 light-years from its core. The oldest clusters in the Milky Way are about the same age. These clusters formed shortly after the beginning of the universe. They provide astronomers with an early record of galaxy formation. G1 is home to several generations of stars of varying metallicity. Seemingly too massive to be an ordinary cluster, scientists believe it to be the nucleus of a dwarf galaxy whose outer parts were assimilated by Andromeda long ago. It has a mass of around 10 million solar masses and a magnitude of 13.7. It is twice as bright as Omega Centauri, the brightest globular cluster in the Milky Way. It is thought to contain an intermediate black hole, i.e. one between a supermassive and a stellar black hole, with a mass of 1,000 solar masses. A globular cluster is denser than an open one. It contains around 10 stars per cubic light year, compared with 1 for an open cluster. An open cluster is a homogeneous grouping of 100 to 10,000 stars of the same age, gravitationally bound together. A globular cluster is also older, often exceeding 10 million years. That's why globular clusters have seen the beginnings of the universe. The stars they contain can be observed individually using powerful telescopes such as Hubble or the Very Large Telescope. Sometimes amateur astronomers join forces with researchers to make great discoveries and advance their knowledge. Thousands of photos taken by enthusiasts bring to light previously undetected objects. In August 2022, for example, 3 astronomy enthusiasts discovered the O3 arc. They observed the same object for 22 nights from August to October. The images show a blue streak above the Andromeda Galaxy. This nebulosity had escaped everyone's notice, yet it's as large as 2 full moons, a third of the size of the M31 galaxy. It is certainly a cloud of ionized gas. Whether it's a segment of the arc of an ancient planetary nebula or the residue of a galactic supernova is not yet known. There may even be another explanation. The arc near M31 is thought to have been formed by violent interactions between stellar currents and tides due to galactic mergers around Andromeda. Some believe it to be located midway between the Milky Way and the Andromeda Galaxy, and to be the result of an interaction shock between the 2 halos. To gain a better understanding of the distant Andromeda, scientists are combining the wavelengths of hydrogen and oxygen. The result is a blaze of color, revealing details never seen before. For example, they have seen a flower-shaped nebula that is still the size of the Small Magellanic Cloud. They have also discovered a pillar measuring several thousand light-years, which seems to rise straight out of the galaxy's core. But there's so much more to discover. Let's move away from Andromeda and pay a visit to its neighbors. Many dwarf galaxies are found around large galaxies. This is as true of the Milky Way as it is of Andromeda. The latter would have devoured these galaxies, and their remnants would now form satellite dwarf galaxies. Over 25 researchers took part in the Pan-Andromeda Archaeological Survey, or PANDAS project. They have detected new dwarf galaxies around Andromeda and determined their distances. Thanks to the Canada-France-Hawaii telescope, they have spotted 2 satellite galaxies that may contain up to 1 billion stars. At least 27 dwarf galaxies orbit M31. The brightest, which I've already told you about, is M32. The second brightest is M110, also known as NGC 205. Charles Messier discovered it in 1773. It's an elliptical dwarf galaxy belonging to the local group and located about 2.7 light-years from the Sun in the constellation of Andromeda. It is not thought to contain a supermassive black hole. It has an apparent magnitude of 8 and contains 24 planetary nebulae. M110's interstellar medium contains significant quantities of molecular and ionized gas, as well as dust, which is unusual for this type of galaxy. It also has a non-zero net angular momentum, unlike the stars that make up this galaxy. This means that the stars follow random trajectories, whereas all the components of the interstellar medium are animated by an overall rotational motion. There are several globular clusters, all made up of old low metallicity stars, with the exception of one. This one, located at the heart of the M110 galaxy, contains blue stars, which are younger and richer in heavy elements. Andromeda's satellite galaxies include the spheroidal dwarf Cassiopeia galaxy Andromeda 7, 2.49 light-years from the Sun, Andromeda 1, Andromeda 2, and Andromeda 3, discovered in 1972 by Sidney Vandenberg. They are spheroidal dwarf galaxies. Andromeda 6, or Pegasus spheroidal dwarf galaxy, located in the constellation of Pegasus. Andromeda 8, 2.7 light-years from the Sun. Andromeda 9, 2.5 light-years from the Sun. Andromeda 10, a little further away, 2.9 light-years from the Sun. I could go on like this all the way to Andromeda 29, but I think you get the idea. A galaxy is classified as a spheroidal dwarf based on its shape and size. If its stars have a roughly spherical distribution, and it consists of a few million to a few hundred million stars, it falls into this category. In 2006, researchers announced that the Andromeda Galaxy's faint companion galaxies lie in or near a single plane through its center. There are 13 of them. They would therefore be aligned, which is strange and unexpected. This plane is 52,000 light-years across and 35,000 at its thinnest. Scientists have yet to find an explanation for this phenomenon. Satellite galaxies to the north of M31 are moving away from the Earth, while those to the south are moving closer. Some believe that the accretion took place along filaments of matter that were aligned on the same plane. Alternatively, the dwarf galaxy disk could be the result of a large gas-rich galaxy generating a series of tidal dwarfs. As you know, the Andromeda Galaxy is heading towards the Milky Way. But what happens when they meet? The two galaxies are hurtling towards each other at a speed of around 120 kilometers per second, or 75 miles per second. These figures are mind-boggling, yet it will take 4.6 billion years for the collision to occur. This gives you an idea of the immensity of the galaxy. The collision will take place because researchers have calculated that the Andromeda Galaxy is heading straight towards our own. Recent observations even indicate that the Triangulum Galaxy will join them to form a kind of super galaxy. This titanic galaxy already has a name, Milkomeda, a fusion of Milky Way and Andromeda. The name was coined by astronomers Thomas Cox and Abraham Loeb. But what exactly will happen? During the encounter, millions of stars will be projected into extragalactic space, hundreds of thousands of light-years away. The result will be a gigantic cosmic fireworks display that can be admired from Earth. Red, yellow, and blue stars will intermingle. Milkomeda will be born from the merger of the two galaxies. It will be an elliptical galaxy of several hundred billion stars. Elliptical galaxies are spheroidal concentrations of billions of stars, resembling large-scale globular clusters. They have a very small internal structure, and the density of stars decreases with distance from the center. Their characteristics are as follows. The movement of stars is random, unlike in spiral galaxies. They contain a low concentration of interstellar matter and gas, so few new stars are formed. They are made up of old stars. First, there will be an initial collision during which the Milky Way's disk will be severely disrupted. The two spiral galaxies will then slowly circle and merge, becoming one in 7 billion years' time. The spiral arms will twist, distend, and draw closer together under the effect of enormous gravitational forces. Bridges of stars will unite the two galaxies. clouds of gas will gather, compress, and eventually collapse, giving birth to myriads of stars. The most massive, barely born, will explode in streams of light. The lightest will cling to the sky. The hundreds of billions of stars that populate the two galaxies will survive, protected by the enormous distances that separate them. However, they will slowly coalesce into a gigantic sphere at the center of which will be a colossal black hole, a union of those that reigned at the center of Andromeda and the Milky Way. In 4 billion years maximum, the Earth and Sun will still be here, even if the Sun will have transformed into a red giant. The Sun may even have left the Milky Way by then, as there is a 3% probability that it will be captured by M31 before the final merger. Scientists even estimate a 12% chance that the Sun will be ejected more than 60,000 light-years from the center of our galaxy. This probability increases with time, so there's a good chance that the Sun will be more than 100,000 light-years from the Milky core after 5 billion years of evolution. Some even think that with all this light, the Earth will have no more nights. The new galaxy thus created will continue to move towards the Great Attractor, as the two still separated galaxies are already doing. The Great Attractor is a region of the universe that draws towards it not only the Laniakea supercluster at a speed of 630 kilometers per second, or 390 miles per second, but also hundreds of thousands of other galaxies. This is made possible by its immense gravitational pull. But some researchers also believe that we are being pushed back by another region of the universe which is emptying out. Galaxies are moving away from the empty regions towards the more massive ones. M31 has already begun its feast, since some remnants of this early meal are visible all around it, in the form of very faint galaxies or diaphanous stellar trails. A team of researchers has embarked on an ambitious project to survey M31's archaeological environment. Since the Andromeda Galaxy is set to engulf the entire local group, it must be interesting to understand how it has grown so far. It's in the halo that the memory of galaxies lies, far from the disk and its permanent agitation. The star streams in the halos tell the story of past collisions. Our great journey is coming to an end. It is unthinkable for the time being to send a space probe, let alone a human mission. It would take millions of years to get there. At the speed of light, it would take 2.5 million years to get there. But no spacecraft goes at that speed. The American space shuttle orbits the Earth at 28,000 kilometers per hour, or 17,000 miles per hour. It would take it 10 billion years to reach the Andromeda Galaxy, which will no longer exist by then. So we're going to carry on doing what we've been doing for a long time, observing from afar. With advances in science and increasingly sophisticated instruments, we can deepen our knowledge without moving. One of the missions that will provide us with answers over the next few years is Athena. Athena stands for Advanced Telescope for High Energy Astrophysics. It's a project led by the European Space Agency. It will be the largest and most ambitious X-ray telescope ever built. Its launch is scheduled for 2031. It will be able to probe the cosmos 10 to 100 times more deeply than previous X-ray missions. It will observe the hottest and most energetic celestial objects. For the time being, scientists have to develop and test a full-scale demonstrator in order to validate the feasibility of such a mirror. The main aim of this project is to answer the following questions. How does matter come together to form the large-scale structures we see today? How do black holes originate, evolve, and shape the universe as we observe it? The Space Observatory will also be equipped with a high spectral resolution spectroimager, with a spectral resolution 50 to 60 times more powerful than what currently exists. If this works out as planned, the leap forward will be significant. We look forward to the new discoveries this program will bring. We haven't mentioned exoplanets in Andromeda simply because they don't shine and therefore can't be spotted from so far away, unlike stars. But it's very likely that future giant telescopes over 30 meters in diameter will discover them in the nearest galaxies. The European Extremely Large Telescope, ELT, should also bring major advances in astronomy. It is a ground-based telescope with a primary mirror 39 meters in diameter. It will collect 15 times more light than existing telescopes and provide images 15 times more detailed than those of the Hubble telescope. It is located in northern Chile. It will be the world's most powerful ground-based telescope. It will enable us to observe the first galaxies and exoplanets. Its observations should provide a wealth of answers to the questions we ask ourselves, but are unable to answer for lack of sufficiently powerful instruments. Commissioning is scheduled for 2027. As you can see, space research is in full swing. We're likely to learn a lot in the next few years. Our knowledge of black holes, star formation, and even the formation of matter is going to progress. And we're bound to make some surprising discoveries, as is always the case in space research. Superclusters are of interest to scientists not only because they enable them to study the expansion of the universe, but also because they help them to understand the organization of matter in space. To study the structure of galaxy clusters, scientists have developed a method based on Hubble-Lemaitre's law. This method reveals the actual distribution of clusters in the universe, without the results being distorted by projection effects. Hubble-Lemaitre's law has made it possible to measure the distance to very distant objects. This law states that galaxies in the observable universe move away from each other at a speed roughly proportional to their distance. This means that the further away a galaxy is from us, the faster it seems to be moving away. To measure the distance of distant objects using Hubble-Lemaitre's law, scientists first perform a spectral analysis of the light emitted by the celestial body under observation. They then determine its redshift, before deducing its recession velocity, i.e. the speed at which the object is moving away from an observer due to the expansion of the universe. Scientists then use the recession velocity to calculate the distance to the object under study. While all this may sound simple, it can be very complicated with distant galaxies that reflect very little light. It can be difficult to obtain a spectrum of good enough quality to be usable. In any case, scientists have discovered that the distribution of matter on a large scale remains rather inhomogeneous. In other words, the superclusters are not evenly distributed, and there are huge gaps between some superclusters, which are spaces without galaxy clusters spanning several hundred million light-years. Astronomers have come to the conclusion that there are over 90% voids in the universe, and that galaxy superclusters are at the border between these voids, rather than the other way around. In fact, galaxy superclusters cluster together in filaments that form the contours of these vacuum bubbles. This reveals that the structure of the universe is far more complex than previously imagined. The origin of this structure is one of the questions that most fascinates today's astronomers, and they're hoping to get some answers thanks to the observation of superclusters. To explore the Virgo supercluster, we have to leave our solar system, then our Milky Way galaxy, then the local group, the group of galaxies in which the Milky Way lies. The local group is one of the groups of galaxies that make up the Virgo supercluster. We are now at the heart of this supercluster, some 200 million light-years across. The Virgo supercluster is also known as the local supercluster. It's called the Virgo supercluster because it contains the Virgo cluster at its center. The Virgo cluster is located around 65 million light-years from us. The discovery of the Virgo supercluster was a gradual process. In 1863, William and John Herschel published the first major collection of nebulae, revealing that a large number lay in the region of the Virgo constellation. Nearly a century later, the Franco-American astronomer G.H. de Vaucouleurs then hypothesized that this excess of nebulae was in fact a galaxy-like structure, but on a larger scale. In 1953, he called this structure a local supercluster, and in 1958, a local supercluster. In the 1960s and 1970s, the scientific community was not yet unanimous on the nature of this structure, which could just as well be a random alignment of galaxies as an ordered structure. In the 1970s and 1980s, a redshift analysis showed that it was indeed a structure. The mass of the local supercluster was estimated at 10 to the 15th power solar masses. Much of this would be dark matter, since the supercluster's luminosity seems very low in relation to the number of stars in it. Contrary to long-held belief, the Virgo supercluster is not a gravitational structure with a clear boundary. In fact, the galaxies in this supercluster are not gravitationally attracted to the center of the structure, the Virgo cluster. Instead, they are attracted to a strange object outside this structure called the Great Attractor. We'll come back to this at the end of our journey. Incidentally, the Virgo supercluster is only a portion of a larger whole called Laniakea. Superclusters therefore appear to be structures of galaxies attracted to a large attractor, rather than structures of galaxies gravitationally bound together. Let's take a moment to study the structure of the Virgo supercluster before exploring its galaxies. In 1982, American astrophysicist Brent Tully illustrated the basic structure of the local supercluster. It would consist of a disk and a halo. The disk is roughly the flattened shape of a pancake and contains 2/3, or around 60%, of the supercluster's luminous galaxies. It includes 3 galaxy cluster subgroups: the Virgo cluster, the Hound cloud, and the Virgo II cloud. The halo comprises 1/3 of the remaining elements, including many elongated objects. It's a more or less spherical halogen atom. The eastern local supercluster has no high-density nucleus. Where is the local group, and therefore our galaxy, located in this immense structure? The local group is located near the edge of the supercluster, in a small filament. It is attracted by the Virgo cluster, not the center of the supercluster. We're now going to look at the galaxies in the local supercluster. Astronomers have noticed that the elements of this supercluster are not arranged randomly. The density of galaxies decreases with the square of the distance from its center, located near the Virgo cluster. The majority of bright galaxies, i.e. those with an absolute magnitude greater than -13, are concentrated in just a few clouds. In fact, just 11 clouds concentrate 98% of the bright galaxies, including the Hound Cloud, the Virgo Cluster, Virgo Groups 2 and 3, and Leo Group 2. All in all, there are some 10,000 galaxies in the local supercluster, spread across some 100 clusters. Let's begin our journey into the heart of the Virgo supercluster by exploring the local group, where our galaxy is located. The local group is located on the outskirts of the Virgo supercluster. It comprises more than 50 galaxies. It is not possible to determine with certainty the number of galaxies in this group, as some are very faint and therefore difficult to detect, and the boundaries of the local group are not yet precisely defined. It is estimated to extend over a diameter of around 10 million light-years. In fact, it's considered a small structure, even if this may surprise you. So there could be far more than 50 galaxies in the local group, perhaps 60 or 80. What we do know is that the local group is organized around two spiral galaxies, the Andromeda Galaxy, or M31, and the Milky Way. Each of these two spiral galaxies is surrounded by satellite galaxies. For example, the galaxy closest to the Milky Way is the Great Dog Galaxy, located just 25,000 light-years from our own galaxy. A third spiral galaxy has been observed in the local group, the Triangle Galaxy, or M33. It is considered a satellite galaxy of the Andromeda Galaxy. In the local group, you can also observe two Magellanic spiral galaxies, i.e., single-armed spiral galaxies, the Large Magellanic Cloud and NGC 3109. These galaxies are smaller than ordinary or barred spiral galaxies. You can also observe an elliptical galaxy, M32, also a satellite of the Andromeda Galaxy. Elliptical galaxies contain only old stars, so according to astrophysicists, they are the result of the collision of two spiral galaxies. The local group also contains two dwarf elliptical galaxies, M110 and NGC 147. All the other galaxies in the local group are either spheroidal dwarf galaxies or irregular galaxies. Spheroidal dwarf galaxies are small, more or less spherical galaxies, often found in galaxy clusters. They are ancient galaxies that closely resemble globular clusters. Irregular galaxies, on the other hand, are neither spherical, elliptical, nor spiral-shaped. They are very luminous, rich in bright stars, but often too small to be easily detected. According to astronomers, they were once very numerous in the universe, but collisions have reduced their numbers. As a result, they now make up just 10% of the galaxies in the observable universe. Let's take a look at the Andromeda Galaxy, the largest galaxy in the local group. With a diameter of 220,000 light-years, it is larger than the Milky Way. It contains 2 to 5 times as many stars as the Milky Way, i.e., around 1,000 billion stars. As a result, it is 25% brighter than our own galaxy. But perhaps this won't last, as the Milky Way's star formation rate is 3 to 5 times higher than that of the largest galaxy in the local group. The Andromeda Galaxy is located in the Andromeda constellation, 2.55 million years from us. You can observe it with the naked eye from the northern hemisphere. It is thought to have been formed by the collision of two galaxies not so long ago. Astronomers estimate its formation date at less than 3 billion years ago, at a time when the Earth already existed. The Andromeda Galaxy and the Milky Way are approaching each other and will collide in around 4.5 billion years' time. The two galaxies will then merge to form a giant elliptical galaxy, along with their two central, supermassive black holes. The Andromeda Galaxy includes numerous satellite galaxies, notably the Triangulum Galaxy, the third largest galaxy in the local group. The two are separated by a distance of 750,000 light-years. This galaxy is unusual in that it has an HII region at its center, rather than a supermassive black hole, which is the most powerful X-ray source in the local group. The Milky Way, the second largest galaxy in the local group, is home to between 200 and 400 billion stars and over 100 billion planets. The solar system is located on the periphery of the galaxy's center, the supermassive black hole, Sagittarius A, precisely 27,000 light-years away. It's interesting to note that the Sun takes around 250 light-years to circle the center of the galaxy, so it's only been around 20 times since it came into existence. Our galaxy formed longer ago than the Andromeda Galaxy. Astronomers estimate its formation at 800 million years after the Big Bang. The oldest star in the Milky Way, HE 1523-0901, is thought to have formed shortly after the Big Bang, 13.2 billion years ago. Among the Milky Way's satellites is the Big Dog dwarf galaxy, the closest to us, located just 25,000 light-years away. This irregular dwarf galaxy contains just 1% of the Milky Way's stars and is being blown to smithereens by the tidal forces of the Milky Way. It is very likely that in the future it will disintegrate completely. The closest group of galaxies to the local group is the Sculptor group, or Sculptor filament. This group includes the irregular galaxy NGC 55 and the spiral galaxies NGC 247, NGC 253, NGC 300, and NGC 7793. All are very bright, although you won't be able to see them with the naked eye from Earth. Irregular galaxy NGC 55 lies at the boundary between the Sculptor filament and the local group, and is therefore the closest to us, at a distance of around 6 million light-years. It contains many stars in formation. NGC 253 is the dominant galaxy in the Sculptor filament, being the largest and brightest. You may have already seen the image taken by ESO's VISTA telescope at the Paranal Observatory in Chile. This image is impressive for its sharpness and precision. It's probably the most detailed wide-field image ever made of the Sculptor's filament. VISTA can see through the dust thanks to its infrared vision, resulting in a sharp, precise image. NGC 253 is also known as the Silver Dollar or Silver Coin Galaxy. It is an intermediate spiral galaxy located in the southern constellation of the Sculptor, around 11 million light-years from us, It was discovered by German-English astronomer Caroline Herschel in 1783 while searching for comets. From Earth, you can observe it with binoculars, as it's one of the brightest galaxies in the sky after our neighbor Andromeda. You can see it from the edge and make out its spiral arms and luminous core. NGC 253 is a good example of a starburst galaxy, i.e., a galaxy that is forming stars at a high rate. This process was probably triggered by numerous supernova explosions. In fact, you can see many bright clusters scattered around the galaxy. They're a kind of star nursery. You can see very young, hot stars that have just ignited, baby stars as it were. In the famous photo of NGC 253, we can clearly see that the radiation from these newly formed stars makes the surrounding clouds of ionized hydrogen glow. NGC 247 is also part of the Sculptor group. It is a faintly barred intermediate spiral galaxy in the Whale constellation. It was discovered by the German-British astronomer William Herschel in 1784, the brother of Caroline Herschel, who discovered the Sculptor galaxy. This galaxy is relatively unknown, as it is rather difficult to observe and photograph. A large instrument would be needed to obtain an image with enough contrast to clearly distinguish the galaxy. NGC 7793 is also a spiral galaxy in the Sculptor filament and the Sculptor constellation. It is one of the brightest galaxies in the group. Studies carried out by the Chandra Space Telescope have shown that this galaxy contains 22 X-ray sources, the majority of which are located in the Eastern Hemisphere. This may be explained by interaction with a nearby galaxy in the past. Before we set off to discover another group of galaxies close to our local group in the Virgo supercluster, let's take a look at the Sculptor dwarf galaxy, which was the first spheroidal dwarf galaxy to be discovered orbiting the Milky Way. Long thought to be part of the Sculptor filament, it is now considered a satellite galaxy of the Milky Way. It is thought to be located around 280,000 light-years from Earth, but was only discovered relatively late, due to its low luminosity. The galaxy contains stars that are poor in heavy elements and therefore old. It is therefore an interesting galaxy for astronomers, as it may reveal valuable clues to the history of the earliest periods of star formation in spheroidal dwarf galaxies. We will now explore the IC 342 Maphei group, another group of galaxies close to the local group. Like our galaxy group, it is organized around two substructures made up of massive galaxies, IC 342, and the pair formed by the two galaxies, Maphei 1 and Maphei 2. IC 342, also known as Caldwell 5, is an intermediate spiral galaxy located 11.4 million light-years from us in the Giraffe constellation. It is the most luminous and massive galaxy in the group. It was discovered in the 1890s. Like NGC 253, it is a star-forming galaxy. The IC 342 subgroup includes 9 known satellite galaxies, including NG 1560, the Giraffe A galaxy, also known as Camelopardalis A or Cam-A, and the Giraffe B galaxy, also known as Camelopardalis B or Cam-B. Maphei 1 and Maphei 2 are located in the constellation Cassiopeia. They were discovered rather late by Italian astronomer Paolo Maffei in 1968. Their discovery was not easy, as they were both hidden behind the plane of our galaxy and therefore partly obscured by interstellar matter. Mephi 1 is the closest of the large elliptical galaxies to us, while Mephi 2 is a spiral galaxy with a very pronounced bar. Like IC 342, the Mephi 1 and Mephi 2 pair has 9 known satellite galaxies, including Dwingaloo 1 and Dwingaloo 2, a barred spiral galaxy and its satellite, a small irregular galaxy. Both are located in the Cassiopeia constellation and were discovered late in 1994. Indeed, they are located at very low galactic latitude, in the avoidance zone, i.e. the area of the sky that is heavily obscured by the dust of the Milky Way. We're now in the Big Dipper. What you're looking at is the group formed by the galaxy pair M81-M82 and NGC-2403. M81 and M82 were discovered in 1774 by German astronomer Johann Elert Bode. Spiral galaxy M81 is the largest of the group, with a diameter of around 87,000 light-years. Although it can't be seen with the naked eye from Earth, it remains one of the brightest galaxies in the sky, which you can observe with binoculars. M82, also known as the Cigar Galaxy, is also a spiral galaxy. It is 5 times brighter than the Milky Way, and even 100 times brighter at its center. And with good reason. M82 is a veritable nursery of stars. A few million years ago, it is thought to have brushed against M81, triggering a huge wave of star formation in this galaxy. It's the closest star-forming galaxy to Earth, so it's much studied by astronomers. It was also in this galaxy that astronomers discovered the brightest pulsar known to date, the ultra-luminous X-ray source M82X2, in 2014. M82X2 is located 12 million light-years from Earth and emits an energy equivalent to 10 million times that of the Sun. M81 and M82 are in close gravitational interaction with NGC 3077, causing the formation of atomic hydrogen filaments between these galaxies. NGC 2403 is the second most important galaxy in the M81 group. It is an intermediate spiral galaxy discovered in 1788. Half the size of the Milky Way, it is home to numerous star-forming nebulae. You can clearly see its spiral arms, as well as small spots resembling star clusters. This was the first galaxy outside our local group in which a Cepheid was discovered. Cepheids are giant variable stars, or yellow supergiants, 4 to 15 times more massive than the Sun, and 100 to 30,000 times more luminous. 2 supernovas 16 times more luminous than average were also detected in this galaxy in late 2004. At that time, the galaxy's luminosity was more than 500 million times that of the Sun. The M101 group lies between the Big Dipper and Hound constellations. It is centered on the galaxy M101, the closest of the giant spiral galaxies, and contains at least 80 galaxies. M101 has a diameter of over 250,000 light-years, twice that of the Milky Way. It is one of the 10 largest galaxies in the Virgo supercluster. It is also known as the Windmill Galaxy, or NGC 5457. Viewed from the front, when he discovered it, astronomer Pierre McCain described it as a starless nebula, very dark and very large. Yet M101 is said to contain 1,000 billion stars, 10 times more than the Milky Way. This group of galaxies also includes M51, or the Whirlpool Galaxy. M51 has recently moved closer to the galaxy NGC 5195, scattering billions of stars from NGC 5195 into intergalactic space and accentuating M51's spiral arms. NGC 5474 is also in the M101 group and may have collided with this galaxy in its recent history. It is a deformed spiral galaxy. Its nucleus is now very far from the center of its disk. NGC 5204 is a small, Magellanic spiral galaxy that emits a very powerful, ultra-luminous X-ray source, discovered in 1980 by the Einstein Observatory, whose origin has yet to be identified. It could be an intermediate mass black hole. Finally, the group also includes the intermediate spiral galaxy NGC 5585, which has the particularity of having a much higher proportion of dark matter than other galaxies of the same type. We're now in the Centaur constellation. In front of you is the lenticular galaxy Centaurus A, or NGC 5128. It's the fifth brightest galaxy in our sky, and one of the closest radio galaxies to Earth. As a reminder, a radio galaxy is one in which most of the energy emitted comes from radio waves, rather than the usual components of a galaxy, such as stars, dust, or interstellar gas. Astronomers are therefore carefully studying its active galactic nucleus. In radio waves, Centaurus A extends over 20 times the apparent diameter of the Moon. Observations of this galaxy suggest that it swallowed a spiral galaxy around 500 million years ago, which would explain its intense radio emissions. Centaurus A's appearance is so strange that it wasn't until 1952 that it was classified as a galaxy. Seen from Earth, it resembles a lenticular or elliptical galaxy with a band of dust superimposed. Again, this strange morphology can be explained by the merging of two smaller galaxies in the past. While the bulge of the galaxy contains mainly old red stars, the disk contains over 100 star-forming regions. The Centaurus A galaxy forms a galactic group with the two spiral galaxies, M83 and NGC 4945. M83 is located in the Hydra constellation and is often nicknamed the Southern Windmill Galaxy for its resemblance to M101. At its heart lies a star-forming outburst region, which is disrupted by a supermassive black hole that ingests huge quantities of matter while expelling matter and energy outwards. This is the galaxy that gave its name to the French electronic music group M83. As for NGC 4945, it's a barred spiral galaxy in the constellation Centauri that resembles the Milky Way. There are a few differences, however, which observations have revealed despite the galaxy being viewed from the edge. Its center is much brighter than that of the Milky Way, and it is believed to house a supermassive black hole that also ejects energy into space, while devouring huge quantities of matter. It has a highly active nucleus, meaning that its central bulge emits more energy than quieter galaxies. It is therefore classified as a Seyfert galaxy. We now turn to a spiral galaxy in the Peacock constellation, NGC 6744. It is accompanied by an irregular companion galaxy, NGC 6744A, which superficially resembles one of the Magellanic Clouds. Located 30 million light-years from us, NGC 6744 is considered to be a look-alike of our own Milky Way, although its diameter is twice that of our galaxy. It is one of the largest and closest spiral galaxies to Earth. Its apparent size in the sky is 2/3 the size of the full moon. Like the Milky Way, NGC 6744 has a dense, elongated central nucleus, a disk of dust, and spiral arms. Astronomers have identified at least 6 galaxies that belong to the same group as NGC 6744. Our discovery of the Virgo supercluster continues with the galaxy NGC 7582. This spiral galaxy lies around 70 million light-years from Earth, in the constellation of the Crane. This galaxy was photographed by the MUSE instrument on ESO's Very Large Telescope to study the effect of an active black hole on star formation in a galaxy. Indeed, the central black hole of NGC 7582 feeds an active core thanks to the enormous quantities of energy it releases. The study of NGC 7582 shows that a structure surrounds the central supermassive black hole, diverting the flow of energy from the active core in the form of powerful winds to protect the rest of the galaxy. NGC 7582 is considered a variable active galaxy. In 1998, a sudden and unusual change in its optical emission line spectrum was observed for several months. Among the hypotheses put forward to explain this variation, astronomers considered the capture of a star by the supermassive black hole. Today, however, it is thought to be molecular material orbiting the active center, periodically occulting it, which gives rise to these variations. NGC 7582 is also thought to be a star-forming galaxy, with one strong burst occurring 6 million years ago and another 1 billion years ago. NGC 7582 is part of the Crane Quartet with 3 other galaxies, NGC 7599, NGC 7590, and NGC 7552. We're now in the constellation of Perseus. You're looking at the barred lenticular galaxy NGC 1023, discovered in 1786 by William Herschel. It's one of the brightest galaxies to be seen, just outside the Milky Way. With a diameter of around 60,000 light-years, it contains a supermassive black hole of around 44 million solar masses at its center. It's small enough to be difficult to see from Earth. You'd need a small telescope, a clear, pollution-free sky, and a time when the moon is faint or distant. The NGC 1023 group includes at least 19 galaxies in the Perseus, Andromeda, and Triangulum constellations. Most of these galaxies are either small spiral galaxies or dwarf galaxies. For example, spiral galaxy NGC 891 is the largest galaxy in the NGC 1023 group, with a diameter of 131,000 light-years. Seen from the edge, this galaxy in the Andromeda constellation is best known to astronomers for being the site of one of the brightest supernovas ever observed, SN 1986J. This supernova, discovered on August 21, 1986, had an apparent magnitude of 14. The Virgo cluster is located at the center of the local supercluster. According to astronomers, it is the largest group of galaxies within a radius of 100 million light-years. The cluster is thought to contain between 1,300 and 2,000 galaxies, including 150 large galaxies and a large majority of dwarf galaxies. The diameter of the Virgo cluster is 15 million light-years. Even the local group is smaller than the Virgo cluster and is gravitationally attracted to it. The Virgo cluster is organized around three main subclusters formed by the galaxies M87, M86, and M49. M87 is the largest galaxy in the cluster, with a diameter of 120,000 light-years. This giant elliptical galaxy contains over 10 billion stars, a supermassive black hole of 6.5 billion solar masses, and more than 10,000 globular clusters. M87 is surrounded by numerous satellite galaxies, including M98, M99, and M100, and the pair of galaxies known as the I galaxy. As for the elliptical galaxy M86, it has the particularity of approaching the Milky Way at high speed. In fact, it's the second fastest approaching galaxy after M90, at a speed of 227 kilometers per second, or 140 miles per second, according to the NED database. It is also said to contain almost 3,800 globular clusters. Finally, the third major elliptical galaxy in the Virgo cluster is M49. It's smaller than M87, but still quite large, with a diameter of 124,000 light-years. Far from the cluster's center, it is nevertheless the brightest galaxy, and therefore the first to have been discovered in the Virgo cluster. It contains some 200 billion stars and 6,300 globular clusters. The M49 group contains more than 120 galaxies in the Virgo and Bernice constellations, including the elliptical galaxy M60, which astronomers believe could constitute a fourth subcluster in its own right. In the Big Dipper constellation on the flank of the Virgo cluster, we find a group of galaxies known as the Big Dipper cluster or Big Dipper group. Its luminosity is 30% that of the Virgo cluster, and its mass only 5%. This cluster forms a ribbon of galaxies in the northern hemisphere, most of which are spiral galaxies. The Big Dipper cluster is made up of two main groups. Ursa Major North comprises most of the cluster's large galaxies, located above 50 degrees north. This boundary remains rather arbitrary. The three brightest galaxies in the Ursa Major North group are NGC 3631, NGC 3953, NGC 4088, and M109. But these are not the only bright galaxies in the group. There are 32 galaxies with a diameter of over 30,000 light-years in this group. The second group in the Big Dipper cluster is Ursa Major Sud. Schematically, this group comprises galaxies located south of 50 degrees. The three brightest galaxies in the Ursa Major South group are NGC 3675, NGC 3726, and NGC 3938. The Virgo 2 groups are long filaments of galaxies stretching southwards from the edge of the Virgo cluster. In fact, they are a kind of extension of this gigantic cluster of galaxies. The Virgo 2 group begins at the level of the M61 and NGC 4753 groups, which form the southern edge of the Virgo cluster. The filament then passes through NGC 4697 and NGC 4699. It ends 30 million light-years further on, with a group of galaxies centered on NGC 5084, a huge lenticular galaxy seen from the edge. M61 is one of the most remarkable galaxies in this long filament of galaxies. Located on the southern edge of the Virgo cluster, this spiral galaxy seen from the front was discovered by Italian astronomer Barnaba Oriani in 1779 and observed on the same day by Messier, who initially mistook it for a comet. It is also one of the largest galaxies in the Virgo cluster. It is also a star-forming galaxy. 8 supernovae have been discovered in this galaxy to date, the latest in May 2020. The M61 group comprises at least 32 galaxies. NGC 5084 is another remarkable galaxy in the Virgo 2 groups. With a diameter of between 250 and 300 million light-years, this lenticular galaxy is gigantic. In fact, it's one of the most massive galaxies in the Virgo supercluster. Its mass is more than 10 times that of our own Milky Way galaxy. The Virgo 3 groups form a long chain of galaxy groups to the left of the Virgo cluster. It spans more than 40 million light-years. Why such a long distance? It seems that the gravitational pull of the Virgo cluster has contributed to the stretching of this chain of galaxy groups. Astronomers have estimated that the Virgo 3 cluster comprises 8 galaxy groups and 13 galaxies outside these groups. Among the galaxies in the Virgo 3 groups is the spiral galaxy NGC 5248, which is one of the brightest in its region, and the brightest in a small group of galaxies. It has a special feature that has been observed by the Hubble Space Telescope. Around its nucleus are not 1, but 2 star-forming disks. NGC 5364 is a spiral galaxy with very long spiral arms. This feature allows it to be classified as a grand-style spiral galaxy, a title deserved by only 1/10 of spiral galaxies. This galaxy is beautiful to look at, even if its spiral arms are slightly asymmetrical and distorted, certainly due to interactions with a nearby neighboring galaxy. Let's continue our exploration of the Virgo supercluster with the elliptical galaxy NGC 4697, located in the Virgo constellation some 40 million light-years from Earth. NGC 4697 is an active galaxy with a faint core. According to a 2008 study, it contains a supermassive black hole of around 170 million solar masses. It is also home to numerous X-ray sources and is surrounded by a halo of hot gas. These characteristics suggest that this galaxy has had a turbulent past, with supernovae, black holes, and neutron stars belonging to binary star systems, all of which could be the origin of X-ray sources. In fact, a large number of X-ray binaries have been discovered in the galaxy's globular clusters. What's more, since black holes and neutron stars are the final stages in the life of a massive star, astronomers believe that this galaxy was home to many massive stars in the past. The NGC 4697 group includes at least 19 galaxies, including the barred spiral galaxy NGC 4731, which measures over 80,000 light-years across. Its spiral arms contain a large number of young blue star clusters. You may notice that its spiral arms are distorted. This is due to interaction with a giant elliptical galaxy called NGC 4697. In the NGC 4697 group, you can also see a small spiral galaxy called NGC 4775, which also has deformed spiral arms, in addition to an off-center nucleus, and the barred spiral galaxies NGC 4941 and NGC 4948. In the Hound Dog constellation, you can see a vast spiral galaxy whose nucleus is surrounded by a star-forming disk. This is NGC 5033. This magnificent galaxy would have a perfect shape if it hadn't crossed paths with another galaxy during its history, slightly distorting its spiral arms. Its active Seyfert-type galactic nucleus is particularly bright, and is certainly home to a supermassive black hole that absorbs large quantities of matter. The brightness would then be due to the hot gas in the black hole's environment. Observations of this galaxy have shown that the location of the active core does not correspond with the galaxy's kinematic center, i.e. the point around which the galaxy's stars revolve. This would mean that the galaxy has certainly undergone a merger. This shift is certainly the primary cause of the core's brightness. Indeed, the shift between the nucleus and the kinematic center can destabilize the rotation of the gas at the galaxy's center, causing the gas to fall into the nucleus. The gas is then compressed by the enormous gravitational forces of the core center and becomes hot. NGC 5033 forms a pair with another galaxy called NGC 5005, but they are not close enough together for gravitational interaction to cause tidal forces and distort the galaxies. The gravitational interaction between these two galaxies remains fairly weak. In any case, we know that NGC 5033 is part of the NGC 5005 group, along with other galaxies. Astronomers disagree on the number of galaxies in this group, but there could be between 4 and 16 members. Let's continue our exciting journey into the heart of the Virgo supercluster with an exploration of the Hunting Dog Cloud. Also known as the Dogs 1 group, the Canes 1 group, or the M94 group. This cluster of galaxies spans the constellations of the Hounds and Bernice's Hare. It doesn't contain many noteworthy galaxies, so it's only very recently that we've been able to distinguish this group from the many other background galaxies in this region of the sky. In fact, it contains mostly medium-sized dwarf galaxies, ranging from 5 to 25,000 light-years in diameter. The largest galaxy in the Canes 1 group is the spiral galaxy NGC 4244, with a diameter of 65,000 light-years. This galaxy is seen from the side. Spiral galaxy NGC 4395 is a good example of a Seyfert galaxy, with a very bright core and faint spiral arms. However, it remains very faint and therefore difficult to observe. In the Dog 1 group, you'll also be able to observe NGC 4214, a small, irregular, hydrogen-rich star-forming galaxy of interest to astronomers because it contains stars in various stages of formation. Observations of this galaxy have shown complex patterns of glowing hydrogen formed during the starbirth process, but also clusters of much older red supergiant stars. Before continuing our journey, let's take a look at the spiral galaxy M94, which gave its name to the dog group 1, also known as the M94 group. It lies at the far end of the cluster and has a diameter of 30,000 light-years. It's a star-forming galaxy that's magnificent to observe. Yes, not only is it seen from the front, but it also boasts a beautiful ring of bright blue stars and well-defined spiral arms. In any case, astronomers haven't yet tired of observing it, and are currently trying to unravel the mysteries of its starry outbursts. The hunting dog's cloud should not be confused with the Dogs 2 or Canes 2 group, which lies behind it. Also in the Hounds constellation, this galaxy cluster contains a remarkable galaxy, M106. Discovered by Pierre McCain in 1781, it wasn't added to Messier's catalog until 1947. And yet, this galaxy is particularly large and bright. It is 130,000 light-years across, larger than our own Milky Way. Its morphology is unusual. 2 spiral arms are clearly visible, detached from the rest of the galaxy, which is not very bright. The most precise images of this galaxy show that it may actually have 4 spiral arms. It is not known, however, whether these 2 additional arms are made up of stars or simply gas. In the same images, impressive jets of matter can be seen on either side of the nucleus, indicating that M106 is a Seyfert galaxy with an active nucleus and that it contains a particularly active supermassive black hole at its center. The galaxy NGC 4217, often presented as a companion galaxy to M106, appears smaller but is in fact of equivalent dimensions. It's simply not as close to us as M106. However, it's not certain that it's really a companion to M106, or even that it belongs to the Canes 2 group, as some measurements estimate it to be 60 million light-years away from us, further from M106 than it is from the Milky Way. We're now in the Lion constellation. You're looking at the Leo 1 group, which is made up of 3 subgroups. On the right, the M96 subgroup, and on the left, the M66 group, and in the middle, the galaxy NGC 3489. The M96 group includes M96 and M95, 2 barred spiral galaxies, and NGC 3377, an elliptical galaxy. All 3 are particularly bright. M96 and M95 were both discovered on the same evening, March 20th, 1781, by Pierre McCain. They are slightly smaller than our own Milky Way. Both feature an inner star-forming disk close to the nucleus, whose secrets astronomers are trying to unravel, in particular, the links between these disks and the central black tower and spiral arms. Let's take a look at the M66 group. It's also known as the Lion Triplet. It includes galaxies M65, M66, and NGC 3628. Their magnitudes make them easy to observe, especially M65 and M66, which are often photographed together, making the Lion Triplet the most beautiful group of galaxies in the Lion constellation. M65 is a spiral galaxy, and M66 a barred spiral. As for NGC 3628, it's a magnificent spiral galaxy seen from the edge, with clearly visible dust bands. We can also see a trail of stars that have been torn from it by the gravitational forces between the 3 galaxies. In the past, interactions between NGC 3628 and M66 strongly affected the morphology of M66, which now has a more elongated spiral arm and a more diffuse halo. NGC 3489 is located in the Leo 1 group, between the two subgroups of M96 and M66. This lenticular galaxy interests astronomers for its hybrid characteristics. It has a prominent galactic bulge and a visible central disk, like spiral galaxies, but no spiral arms. It also borrows characteristics from elliptical galaxies, with little ongoing star formation and stars over 1 billion years old. Like many of the galaxies in the Virgo supercluster, it is a Seyfert galaxy with an extremely bright core and a central black hole that devours any matter approaching it. The radiation from its active galactic nucleus, however, is weaker than average. See that vast gathering of galaxies to the right of the Virgo cluster? Those are the Leo 2 groups. These groups of galaxies lie behind the Leo 1 group and are spread over 30 million light-years. The elliptical galaxy, NGC 3607, is the brightest in the Leo 2 group. Among the other brightest galaxies in this area of the sky, you'll also find NGC 3169, a highly distorted spiral galaxy. It can be seen in the Sextant constellation, just below the star Regulus in the Leo constellation. Gravitational interaction with its neighboring galaxy, NGC 3166, has taken its toll on its magnificent spiral shape, and it now looks as if it's completely disintegrating. Astronomers wouldn't be surprised if the two galaxies were to merge. In Leo Groups 2, you can also observe a curiously shaped spiral galaxy, NGC 3187. It features very open spiral arms. As for spiral galaxy NGC 3227, it's glued to dwarf elliptical galaxy NGC 3226. Both are among the 338 galaxies listed in Halton Arp's Atlas of Peculiar Galaxies under the name ARP 94. According to American astronomer Halton Arp, they are a good example of a spiral galaxy with an elliptical companion. However, there is nothing to suggest that they are in fact interacting gravitationally, especially as the distance between them remains relatively large, at around 9 million light-years. Let's continue our journey towards the Furnace cluster. But before we do, let's take a look at a remarkable galaxy called NGC 2997. This grand-style spiral galaxy is located in the constellation of the Pneumatic Machine, a constellation you may not have heard of often since it's located in the southern hemisphere and is relatively faint. NGC 2997 was discovered by William Herschel in 1793 and lies around 55 million light-years from us, but is moving away from us at around 1,100 kilometers per second or 680 miles per second. This galaxy is particularly remarkable for its nucleus, surrounded by a string of giant clouds of ionized hot hydrogen. The NGC 2997 group comprises some 15 galaxies, including several irregular Magellanic galaxies. Before arriving at the Furnace cluster, the Dorado group is also worth a visit. Call it a group, but it's more likely to be a cluster of galaxies given its size. The Dorado group comprises spiral and elliptical galaxies. It is organized around two interacting galaxies, the elliptical galaxy NGC 1549 and the lenticular galaxy NGC 1553. These are the two brightest galaxies after the spiral galaxy, NGC 1566, considered the dominant galaxy in this group. NGC 1566 and NGC 1553 are disk galaxies, which is the dominant galaxy type in the Dorado group. Astronomers therefore consider this group to be even richer than the local group. We're now looking at the Furnace cluster, the only other cluster within 100 million light-years of us that's almost as rich as the Virgo cluster, though still a little smaller. The Furnace cluster is of particular interest to amateur astronomers for its compact core of galaxies, spread over just 2 degrees of sky. The 2 dominant galaxies in the Furnace cluster are NGC 1316 and NGC 1365. They're bigger than any galaxy in the Virgo cluster. NGC 1316 is a massive lenticular galaxy, which according to observations absorbed a spiral galaxy around 3 billion years ago. This was probably not the only galaxy to be cannibalized by NGC 1316. Not far from this galaxy is a spiral galaxy called NGC 1317, which could suffer the same fate. NGC 1316 is also a powerful radio source, known to radio astronomers as Fornax A. It is the most important source of radio waves in the constellation Furnace, and the 4th most intense radio source in the sky. These radio waves come from falling matter inside the supermassive black hole at the center of the galaxy, probably fueled by interactions with other galaxies. NGC 1365 is the best-known galaxy in the Furnace cluster. It is a magnificent barred spiral galaxy of great style. Discovered in 1826 by Scottish astronomer James Dunlop, it lies in the southern constellation of Furnace and is studied by numerous telescopes. Its bluish color is due to a very high rate of star formation. This can be explained by the presence of a bar that connects the 2 spiral arms and compresses the gas present in the galaxy, triggering the birth of multiple stars. The Eridan cluster is another remarkable galaxy cluster in the southern hemisphere. It is sometimes referred to as the Furnace 2 cluster. This is because it is very close to the Furnace cluster at a distance of around 20 million light-years. The Eridan cluster is further away than the Furnace cluster, at around 75 million light-years. These 2 clusters and their surrounding galaxies are sometimes referred to as the Furnace or Deep South superclusters. The Eridan cluster contains around 200 galaxies. Its galaxies are scattered over a larger area than in the Furnace cluster, so it is less impressive than its neighbor. 2 subgroups can be distinguished, one to the south around NGC 1395 and one to the north around NGC 1407. NGC 1407 is a vast elliptical galaxy, larger than the Milky Way, with a diameter of around 243,000 light-years. Its group contains at least 9 galaxies. NGC 1395 is also a vast elliptical galaxy, but slightly larger, with an estimated diameter of around 264,000 light-years. The NGC 1395 group contains at least 32 galaxies. We can't leave the Eridan cluster without a quick look at NGC 1232, one of the most beautiful galaxies in the cluster, with its well-defined spiral arms. This stylish spiral galaxy is around 145,000 light-years across, and its spiral arms contain millions of bright stars, alongside dark dust, to the delight of our eyes. We've taken a tour of the Virgo supercluster. This trip will have given you a glimpse of all the types of galaxies that exist in the observable universe, with near-perfect spiral galaxies and spiral galaxies distorted by the movements of the universe, giant galaxies and dwarf galaxies, active galaxies, and galaxies where no stars are forming anymore. But you should know that the Virgo supercluster won't remain frozen like this for long. The universe may be moving slowly, but it's moving all the same. The Virgo supercluster itself is constantly changing. It is attracted by the Great Attractor, a gravitational anomaly located near the ruler cluster. But what exactly is the Great Attractor? The discovery of the Great Attractor dates back to 1977. American astronomer Vera Rubin and her colleagues at the Washington Institute discovered that the Milky Way was moving faster than the expansion of the universe. The astronomers hypothesized that there was a force with a gravitational effect on the Milky Way, without knowing exactly what it was. A team of 7 researchers from the Cambridge Institute of Astronomy and the Washington Institute of Astronomy was formed to investigate the question. For the record, this team was nicknamed the Seven Samurai. To unravel the mystery of this unidentified gravitational force, the researchers measured the proper velocity of a large number of galaxies in order to determine in which direction the Milky Way and the local group were moving. 400 elliptical galaxies in the Centauri region were studied over a 5-year period. In 1986, the researchers from this small team discovered that the local group, as well as the Virgo supercluster, were moving at a speed of around 625 kilometers per second, or 390 miles per second, towards a point they dubbed the Great Attractor. This point lies beyond the Hydra-Centaur supercluster, in the direction of the Southern Cross, some 150 million light-years away. Scientists have calculated that the gravitational force of this mysterious attractor is equivalent to that of a supercluster, over 10,000 times the Milky Way. And yet, no visible mass has been identified. Here is a spine-chilling anecdote. Foucault's pendulum in the Pantheon in Paris points in the same direction, but no one knows why. An even more mysterious fact. In the region of the Great Attractor, the natural speed of galaxies is that of the expansion of the universe. And once past this fictitious point, galaxies have a speed slower than that of the universe's expansion, and some even show a blue shift. But the presence of the Great Attractor alone cannot explain these speed variations. In fact, other researchers have measured the radial velocities of galaxies in the Perseus and Pisces clusters, which are located further from the Great Attractor than the Milky Way. And it appears that they are drawn faster towards the Great Attractor than our galaxy or even the Centaurus or Hydra clusters located closer to this fictitious point. Researchers have put forward all kinds of hypotheses, including the presence of another Great Attractor or the imprecision of radial velocity measurements due to the uncertainty linked to galaxy luminosity. In 2016, after 30 years of research, researchers identified the existence of large extragalactic structures that could explain the gravitational attraction of galaxies towards the Great Attractor, without, however, completely solving the mystery. We've come to the end of our journey through the Virgo supercluster. But we're not done exploring the universe yet. The Virgo supercluster is part of a larger hole called Laniakea, and Laniakea itself is just one of the 6 million superclusters that exist in the observable universe. So there's still a long way to go before we understand all the mysteries of our universe and its organization. In the meantime, we can marvel at the beauty of galaxies and stars and the way they are arranged in the sky, whether by chance or not.